Hello, and welcome to what may be the final lecture. This is week 10. I've sort of have 2 extra weeks that I want to delineate toward final projects and have the students sort of do the lectures and present their final projects. Or if that doesn't take 2 class periods, we might have another lecture on something the students decide. So I gave them some options in terms of dealing with spatial data, and a few others. I don't remember what else we sort of went over. But hopefully the pacing of the class is good. It's tough because the semester hasn't even started yet and I'm done recording. And so I could be vastly underestimating or overestimating sort of the student ability to digest information. But hopefully the sort of one Zoom session, in addition to these recorded lectures, has provided a little bit of flex there. All right, so today we'll be talking, exit out of that, so we'll be talking about parallel computing. And so I'll open up the lecture notes in our studio and we can work through them. All right, and I'll go ahead and share my screen. All right, there we go. And so the reading for this week will be Parallel Processing and Large-Scale Simulation, Motivation, and Methods, which talks a little bit about the underlying sort of background for parallel processing. That was written in 1991, and despite that, it still actually has a lot of really relevant information in terms of parallel computing and parallel processing. And so I think a lot of times students see parallel computing as sort of, especially in science, as sort of this abstract bar that they just can't get at or don't need to get at. And so a lot of things, I mean, I've run into this too, where you say, I could leave it running on a single core for a week and it'll finish, or I can parallelize it, which will take a little more effort up front, but it'll be done in a day. And so I'm going to try to argue that the parallelization and having it be done in a day is sort of inherently better. And it's not that hard. The bar is not as high as you think it is. And so these tools are really key, especially for simulation analyses and things where you're doing a lot of processing through, and you may not be able to wait in terms of core hours on one processor core, because it may take months. And so I here introduce sort of what is parallel processing or parallel computing, and I define it as the act of using more than a single core of your processor. And so computers, one that's right down here, and right over there, and over there, I have 3 computers in this house for some reason, generally have more than one core, right? And so even older computers will probably have a dual core processor, which means the processor is there and it has 2 different cores. It can run different processes on it. But most sort of modern processors have 4 to 8 or more. I think maybe we can look at how many this has. I'll open up the terminal. Nope, I told it I'd do things in our studio, and so I'm going to use the terminal in our studio, and we can say htop, and we see this actually has 8 cores for the one processor. These are probably not 8 physical cores, but the delineation between physical core and virtual core doesn't really matter. Basically, I can run at any time 8 sequential processes distributed across these cores. And so we see that core 4 is up to 100%, probably because it's running something in the background. I'm not sure what it's running. But other cores are much less burdened. So let's quit that. All right. And so I think a lot of students might think, when is the best time to parallelize, and also at what point in your code? And so the process of parallelization is basically, so let's say you have something that you want to do Yeah, I gave the example of like thinking of a for loop. And so if you have a vector of vegetables and you want to cut up all of the vegetables. And so this is obviously a conceptual example, less of a programming example. You could write a for loop and say for I in vegetables, cut vegetable. And that will go through and vegetable I, sorry, so index at I. And so that'll go through and say, like, pick the first vegetable, cut it up. Pick the second then, so loop through, now I equals 2, second vegetable, cut it up. And that makes sense to do, but that sort of task is what would be known as embarrassingly parallel, which I have no idea why they call it that. There's a lot of problematic terminology in computer science, in parallel computing even. So the typical terminology for distributing processes is master and slave processes, which is not ideal on many levels. And there's been a whole bunch of things that say like other things we can call them, but I will not use that terminology because it's a bit problematic. So yeah, embarrassingly parallel means that in that conceptual example where I have the for loop where I'm cutting up vegetables, I could just, if I had multiple versions of me, I guess I'm the processor in this situation, or I'm the core. If I had 4 versions of me, I could just hand vegetables to each one of my selves. They can cut the vegetable up. And then if I still have vegetables to go, I can give other versions of me more vegetables and they can cut those up. And you can already imagine why that speed up like the process fundamentally, especially as the number of vegetables I have gets large. All right, and then I talk a little bit about okay, so that's a clear example of when you can parallelize something, but there's also instances where you can't, and so sequential processes. So let's say you're doing some form of gradient descent or optimization problem. That becomes hard to parallelize because that relies on information in the previous step, right? There's probably a better example than that, but it simply is like very, very difficult to parallelize when it's a sequential process. And so like generating a time series, you can't really parallelize that necessarily because like the state at time t is dependent on the state at time t minus 1. And so you have to choose how you would parallelize that. I give some example. For instance, if you have a model that you'd like to run with 1,000 different parameter values and each model is run 10 times, yeah. Okay, so it's at what level you should think about parallelizing conceptually. And so here we have an example where we could parallelize this code either at the level of parameters, so I have 1,000 parameters I want to go through for a model, or we could parallelize at the level of running the model. And so the model will be run 10 times per each parameter value. I say you cannot parallelize both, like it's not like strictly true, but it's clunky and it's not a good idea. And the reason it's not a good idea, and the reason we have to think about where in the code we want to parallelize is because there's overhead involved in parallelizing code. So think back to the conceptual example of me handing out vegetables. In a for loop, I immediately have the next vegetable in my hand and I cut it up. In the parallelized version of cutting up vegetables, there's overhead in terms of I need to hand the vegetable to the core. After the process is done, that core needs to hand the vegetable back to me. And that may sound odd, but like that takes time to move data around. And so for this example, I don't think we'd want to parallelize at the level of of running the model 10 times, depending on how long that takes. Because you also have to think about not just sort of computational demands or memory overhead, but also just time, because that's really what we're trying to minimize and get that speed up in terms of time that it takes to do something. But in this case, I would probably be leaning more toward parallelization at the level of parameters. But maybe that's not the right choice. Yeah, and so now I talk a little bit about why things should be parallelized, things that, situations that sort of inherently limit the speed of your code such that parallelization is a step in the potentially right direction. And there's four, only one of which is really like the main one, which is CPU bound. CPU bound means that the process just takes too much CPU time. The second one is memory bound, which you will run into sometimes in R, but it's hard to get around, because then the parallel computing is more like distributed computing, where different processes occur on actually different nodes or different computers, and therefore you have more memory to flex around. And we won't go into anything like that. There's also these other two, IO bound and network bound, which also I don't foresee that being super duper useful for students. And so I think especially a lot of general issues here will be things that are CPU bound. Yeah, and I can go into sort of memory bound processes and R having to hold everything in memory. Not strictly speaking, you can hold some things outside of memory, as we saw with the lazy evaluation of the API calls in the, was it week 6, R and the API. But we're mainly hitting processes that are CPU bound. And yeah, I've sort of already covered why we would consider parallelization, and the main reason is speed up in terms of time, computational time. And yeah, this becomes especially important when you get into data simulations and things like that. But it also, like, if you write your code in parallel, it sort of pushes you to understand how you're using memory, how you're actually using your machine, and sometimes can make it easier, at least conceptually, to run code on a remote machine. And so we haven't talked about that. That's surprising. I didn't talk anything about running code on a cluster or even SSHing into a remote machine. That's fine though. We may have talked about that by now, just in the Zoom session in class. But that's more of like a computational skill and has maybe slightly less to do with reproducibility. It definitely helps though, because it's a sanity check. Like if I run code on my machine and then I submit to a cluster and it bonks, that sort of means like, hey, that code's not really that reproducible. So I should probably fix that. Okay, but now I'll sort of switch from talking about why parallelization is important and talk more about how we actually do it in R. So how do we cut up the vegetables in parallel? Alrighty. So that's the annoying part, is actually there's a bunch of different packages that you can use to parallelize code in R. I'll mainly focus on the parallel package. And so, and specifically the cluster apply LB function, which I think is the sort of most helpful hammer, if you want to view it like that. It's the tool that sort of I find myself leaning back on and saying like, oh, I can parallelize this very quickly and just use this approach. And it has a similar sort of syntax that you may be familiar with, and that's the syntax of the apply statement. There's also the for each package, which I'll write here if you're interested. And that is structured a little bit more like a for loop. And it's fine. I don't know. It's just different schools of thought, I guess. I always struggle when I try to use for each because it's like a for loop, but then it like blocks into chunks, which is good sometimes and bad sometimes in my mind. And so if I block into chunks of like, if I'm running a model and I block into chunks of parameter value sets, what happens if the time required for this chunk is different than the time required for this chunk? It means that all of a sudden I'm limited in terms of overall computation time by whatever the slowest chunk to complete is. Meanwhile, if you do the cluster apply LB, LB stands for load balancing. And so you're not really confined because all of a sudden your chunks are one iteration or one run of that, of whatever you're reaching through. But you can get around that. That's not a big deal. So maybe check out the for each and see if that syntax sort of makes more sense to you. I think at that point it's sort of personal preference, but I really like the parallel package and the apply statement structure. And so first we'll talk about sort of how to actually just go about setting up your own sort of little computing cluster. It's not a cluster. But how to make your computer recognize that you want to start setting up the parallelization process. And so we can use the parallel package and use the detect cores function, which you don't have to give it any arguments, to see how many cores your machine has. This one says we have 8 cores, and I actually do go into a little bit. So it's a quad-core CPU. So I have a processor that has 4 physical cores, but it's hyper-threaded, so it means it has a total of 8 virtual cores. Doesn't matter. I can SSH into like the lab machine, and it'll say something different, and I'm not going to do that because we haven't even talked about SSH potentially. So it differs per computer, and so run that command and see what it says on your computer, and it'll probably say somewhere between 2 and 16 or 32. 32 if you're a beast, though. Yeah, 64 is like, man, how much did you pay for that? And so now let's run the actual, I'm not going to do the install command because I already have the package installed. I'll pull it in using library in the R code. And now let's just set up a cluster of 2 nodes. And so that'll mean that we have access to 2 cores. I think in general, it's sort of not great practice to make a cluster. Some people say make cluster, and then they just embed it and say detect cores, meaning allow this cluster to have access to every single core of the machine. And it's a decent way to like not go out of memory, but like definitely tax your cores, like, because your operating system and other stuff is using processes, like it's doing stuff. So maybe that's not a great idea, I would argue. So we're just going to set up with 2. So we can enter that. We call it the object CL, which is just like a silly sort of, I don't know, that's what everyone does. They call it cluster. And so we can see the object, and it prints out what it is. It's a socket cluster with 2 nodes on localhost, localhost meaning this machine. All right, and so now I'm going to go into the syntax of cluster apply LB versus just a normal for loop. And how I'm going to do that is a simple benchmarking of just as we did before on API, no, it's testing maybe. I think I talked about this during the unit testing lecture. And that's wrapping the command in system time. And then so here's a for loop that basically says for I in 1 through 5, sleep for I seconds, which means it's going to pause and do nothing for I seconds. And so it's going to start and just sleep for 1 second, then it's going to sleep for 2 seconds, then it's going to sleep for 3 seconds until it reaches 5 seconds. And so this should take around 15 seconds to complete this, because 5 plus 4 plus 3 plus 2 plus 1 is around 15.
2 hours later.
This is why you don't use RStudio. I'm just kidding. Yeah, it shouldn't take that long. Use like the terminal commands. I don't know, how do you quit out of? If I just end it. All right, there we go. That wasn't incorrectly written. I don't know why that. Let's try that again. All right, that's better. Sorry about that. Okay, so now it's going through the for loop. Should take 15 seconds, and then it's going to spit out the wall time and user time and system time, or elapsed time for the for this loop. And it is. It's just a little over 15 seconds total elapsed time. And now what we can do is, instead of coding like that, we can use cluster apply LB. And so this is basically set up like an apply statement where the first argument you hand it is the cluster. Then it's the object you want to apply over. So remember when we learned about apply statements, this would have been maybe a matrix. If you wanted to take and use an apply statement and take like the mean of all columns of a matrix, you would say apply and then hand it that first argument of a matrix. The second argument would be the margin you want to compute over. And so if you want columns, the margin is 2. If you want to compute on rows, the margin is 1. And then you hand it the function. So you could just say mean, or you could write it as defining your own function. And so this is really similar. I just give it a vector of 5, as I did in the for loop up here. And then I give it the function that says sleep for x seconds. So here it says function, and it takes an argument x. And that's the structure of the apply statement, where these values get handed to the function and take that value of x. And so hopefully that made sense. It's hard because I can't like look at students and see if they're like confused looking or not. But so hopefully that is similar in structure to the apply statements that you've seen. Like that's what it should be. And so now we have our code all written out, and we can run it in parallel. We handle our cluster object, we handle everything, and it should take way less time. It shouldn't take 15 seconds, it should take more than like 8 or 9 seconds. It takes 9 seconds. And that's because it handed the 1 core 5 second, the 1 core 4 second, and then it had to wait for the 4 second to be done, hand the 3 second iteration to that core, wait until the 5 second is done, hand that the 2 second, and so there's a little bit of like memory transfer there that made it be a little bit slower than it possibly could have been. No, there's not much memory transfer, because the longest running would be 5, 3, and 1, and 5 plus 3 plus 1 is 9. So actually, yeah, it pretty much just like instantaneously, because it wasn't doing anything that taxing in terms of shuffling memory around. So hopefully that also made sense. Do you see what I tried to do there and break down how it parallelizes the code? Like it has a vector of 5 possible values that it can sleep for. And it's trying to balance those in the best way. And so it hands the first core, it has 2 cores to do that in. So it hands the first core the 1 second wait time, and the second core the 2 second wait time. And then this one, the 1 second wait time is done first, so it hands that one the 3 second wait time. So it's doing it sort of in order. And then this one gets done, and it hands it the 4 second wait time, and then this one gets done, and it hands it the 5 second wait time, which means that the total time for the entire process is basically limited by the slowest of those, which is 1 plus 3 plus 5, which is that core, which is 9 seconds. Cool. That was awesome. So we set up the core, we ran the code, tested it using like the system time to benchmark it, and now we can stop the cluster. And that's good. You always want to stop the cluster. Don't want to leave that running, because that's just weird background noise. I set that to false, but I still did it for the sake of this lecture. But it's okay. I remake the cluster basically every time. And I remake the cluster in the same way. So I do it right here. Oh, and okay. And so parallel code can sometimes, I mean, this isn't a problem with all code, but if I'm using random variables and I'm generating them within some or within a for loop or something that's not parallelized. So it's a problem regardless. We need to set seed. And so I think I know this before, but if not, this is. And so we can do that by handing the setSeed function an index value in the cluster apply LB statement. And so here, this is the same thing as before, where I handed a cluster object CL, I hand it some vector of values or some like array, and then I give it, for each of those values, do this function. Whew, if I was going to sneeze, did not sneeze. Do this function. And here the function takes x, where x is 1 through 5, or one of those values. And now I have this argument to set the seed at that value. So now I know the index and what the seed was set at. So it's reproducible amongst it. Set seed. And I pull those from the uniform distribution. If I close again, they're different. Why is that? Hold on. Oh, I think it's how setSeed works. Yeah, there we go. And so I have to reset the seed basically every time. But that'll always result in the same values. When if I didn't do that and just did RUnif, I get different values each time. Okay. We can run that code. So I did the same thing as before. There we go, it's fine. I don't like RStudio. I'm gonna blame this on RStudio. All right, and now I go into, it's not like a niche example, but it's an example that's trying to get you to think about how you would use parallel computing in your sort of coding situations that you would run into. So I set up this example where above we wanted to make draws from a random uniform distribution. But here I'm basically setting up ways where we can refine those draws from the uniform distribution. And so there I set seed, but I just left everything as base. And so it pulled a random uniform variate between 0 and 1. But we do have the capability of setting a min and a max and a different range, min range, max range. Oh, and the number of values that you want to pull from the distribution. And so here we can set it up rather than handing cluster apply LB, just a vector. A little bit of a hacky way to do it. There's probably many better ways to do it, but this is one way to go about doing this. And it's also to show you some issues in terms of global workspaces versus what the parallel function has access to object-wise. And so we'll set up this params data frame, run it. It's like 5 by 4, 5 rows, 4 columns. It gives its index value, which is just a sequential value starting at 1 and going to n row params. Then we have this number of values column, where this is the number of values we want to pull from the uniform distribution. And then we have the min and max range that we want to consider as we pull from the distribution. And so here I structured this as we cluster apply LB, you hand it the cluster, which I think I made it, yeah, I made it up there. It's still running. And I handed that index. And now I can use that index to actually just to index the values in that data frame. And so I set seed to the index, and then I say run if, and I say params num values, and so that's the number of values that it should generate. And then I set the min and max parameters by using the index of the index variable. So we could run that. Oh, and we see that 5 nodes produced errors. And so this is a common error that you're going to get. This error, check for errors, n nodes produced errors with n all from being a lot of nodes. Because it's the same core that's just like spitting out and being like error, error, error. And so here, every single row that we try to give it, so we have 5 rows, it errors out. And that's informative. And it's also informative because it tells us what the first error was. And it says object params not found, which is weird because like I have params right there. Like, so why is it not finding it? And that's because params only exists in the global workspace. When you think about parallelization, think about the cores as almost being completely independent of your workspace. And so you distribute some process to run in the core. It doesn't see the global workspace. It doesn't have access to those data structures. And we can get around that. We can solve this problem. This is actually just a list object, I believe. We can get around this problem by using cluster export in the parallel package. So we say cluster export. We say that the cluster we want to export these objects or functions or things from the global workspace to each of the cores. And so we just want to hand it params, just one thing. And so we can run that code, and now each core has access to params. And so we can go back up and run this, and it now runs, and everything is hunky-dory, everything's cool. So yeah, be mindful of cluster export, be mindful of that objects in the global workspace, sometimes libraries or specific things that are, you need to call in certain functions. And so that's a challenge to parallel computing, but it's also, it will keep you mindful about what each function requires and about how your computer is actually sort of managing memory and objects, which is really useful, I think. Okay, so we've gone over sequential versus cluster apply LB in the parallel package. And before we sort of shift gears, I wanted to briefly talk about existing functionality for parallelization within the dplyr package. And so dplyr where we learned some of those modified apply statements like ldply and alply and whatever, just many iterations of that. I hesitated on talking about this one because it's going to require another dependency, and also it's a little bit, I'm not sure how stable it is. I'm not sure if they're going to keep up with it, because they had like dplyr for a little bit for working with databases, and I thought they were going to shift a lot of the parallel stuff into that. And they don't really advertise the fact that these apply statements can be run in parallel, so it makes me suspicious that one day they're just going to drop support for it. But it's been around for years now, and I don't know, nobody's really talking much about it. Maybe I'm just not listening to the right people. But so this one uses, you have to have a parallel backend registered, and there's a bunch of different ways to do that. And you'll see that, I think multi-core can do it. There's like, what's that one that says plan? I don't know. There's a bunch of them. We're a little frustrating because more packages, more dependencies, more things to worry about, more things that can break. It's not ideal. And so here, this is essentially the same thing as the as setting up the cluster, but now we can actually stop the cluster. I forgot about that. So let's run that. Stop the cluster. All right, so now we're down, because we're basically going to remake it down here. And that's what the doMC package and register doMC, which MC standing for multi-core, means. And so here, I'm using ldply, and I'm setting up, let's register the cores first. That works. And now let's look at what this is. And so create a list object of length 1,000. So this is a list of 1,000 that each element of the list is 10,000 random draws from a uniform distribution bounded between 0 and 1. And so I put this in just to, I got to further expose you to the structure of apply statements and for funsies. But also it gives us something to work over. And so, and something that should be large enough to where it's going to show the difference between a unparallelized and parallelized statement. And we're going to use ldply. I don't know why. This is basically laply. Oops, capital. This is basically LA-ply, but let's see. Well, let's smash into a data frame just for fun. It'll be a one-column data frame, I think, is the output. And so this should look familiar, and let's be specific about what package it's calling from. I've tried to do that throughout, and I probably have failed, but let's try to generally keep that structure intact. And here at dplyr, we hand it the list object first, and then it has many different arguments that all start with dot. And you can see them in the, oh, I didn't load the package. dplyr. And you have to load plyr first if you're ever using a plyr function. So just in case we use plyr functions later on, you have to call in plyr before you call in dplyr. Which I think if delightful, it's not annoying. So yeah, we can see the different functions that you can hand to it. The most important being .data.fun and .parallel. And then also there's .parops, and you can hand it different parallel options. And I'm not sure all of those, but oh, it has export, so you can just build in your export command directly into that instead of keeping it as a separate function. What does that matter, really? But this one doesn't need any external packages, and so we don't need to worry about exporting anything. And we have our .parallel set as false at first, and we have this parallel backend registered. And so this line will not run in parallel. This line will run in parallel. And we're taking the mean of each list element, and then we're calculating the system time. So how long is each taken? We'll add in some annotation. Not parallel. This is the best annotation. Parallel. Oh, it's in plyr. Ah, my bad, it's in plyr. I should know that actually. So I said, that's also one good reason to like state the package clearly before you do that, is because you'll hit things where like you think it's in one package, but it's actually in another. Oopsies. So we can do in plyr, and we see it ran both. I don't know why. And so the first one took around 0.03 seconds to not run it in parallel. And then we see what happens if you run it in parallel, and it takes an order of magnitude more time to run it in parallel. And so this is a way to both show you how to do it and to caution you against necessarily doing it because of the memory overhead. And so that's why it's so slow. But I mean, I think that would speed up if we handed it more cores. So let's try to do that. So that one's still going to take the same amount of time, and that one takes, yeah, they take the same amount of time. I think that is, yeah, that's just a function of having to move memory around. But it's repeatable, and so it's not ideal. Yeah, and so that's how you can use plyr for parallelization. I almost want to do this really quick in cluster apply LB to see if it does the same thing. Let's do that. We don't have a CL, but we'll make a CL above. We say list, and then let's just give it the function mean. And then we say CL parallel make cluster. Hopefully you're following along with this and I'm not going too fast. Parallel spelled right, cluster apply LB. Let's copy the system time over here, and that should do it. We know we have finished with the cluster one. Oh, I think I said I'm supposed to say now. Why am I where here? What just happened? Object parallel. Oopsies. Tried to make the cluster, failed. There we made the cluster, and it says, what is it doing, man? It's bouncing me all around. I hate our studio. Didn't close the brackets. Yes, that's the reason. See, these are stupid errors that you're just gonna make. So like, this is a good example of, yeah, closing brackets and closing parentheses. don't feel discouraged when you mess it up, because I mess it up all the time. That's running. That's taking way too much time. What is it doing? Something's wrong there. So it took 21 seconds. Why? What? That's weird. Let's try it again. Oops, I made the cluster again. Yeah, it seems that's just going to take that long. I don't know, no idea why it's doing that. But these are results just because it's like there was an open cluster and it closed it. And now it's only taking 12 seconds, which is still a ridiculous amount of time. So yeah, that may boil down to just memory overhead. And so it's definitely something to be cognizant of. But yeah, that's weird. I wonder what plyr is doing differently than cluster apply LB. Oop, and then I already said that, and I already did that, so I said that where I stopped the cluster. And so if you try to stop a cluster and it's already been stopped, it'll just say it's an invalid connection, meaning you can't really find the cluster, it doesn't really exist. Even though in the global workspace, you'll see it still is there. It's a socket cluster, but it's not. It doesn't exist, so let's just remove it. I feel like that was there before. It made all my stuff look weird. All right. And then at the end of this lecture, I don't think I'm like anywhere close to being over time. It's because I didn't really want to go too in depth on a lot of the nitty-gritty of things, but I'm not sure if this is going to be that useful for people. But I think it is useful to think about, and I've shown sort of how you can use parallel programming. And then in the Zoom lecture with the students, we'll go into more detail or talk about like problems that you guys are encountering or how to scale this to a remote machine that has many, many cores to really like get the full punch of parallelization. But since this is like putatively the last class, I wanted to just like give some like tips that I'm sort of and that I find useful while all right. I lost internet for a second there, so hopefully most of this lecture is okay, because that would suck to have to, and I've already had to do that once where it didn't record or it recorded all with bad audio because I'm recording to the cloud. So what I was saying before I was so rudely interrupted was that at the end of this lecture, which is now, I was just going to run through some tips and tricks that I found useful when dealing with R and first sort of learning R. So let's scroll down. Yeah, and many of these things are things that I've already touched on throughout this class, and that I just want to reiterate as we move forward. And a lot of them have to do with just like keeping your projects organized and keeping naming nomenclature the same across projects. So that's for number one, is keep your analytical pipeline completely organized, because like the person that's like worst for your reproducibility and your ability to reproduce your code like 10 years from now is you. Like you're writing the code. If you clearly document your code and you have a clear vector structure, it's going to help so much in allowing you to reproduce your code and hopefully others to reproduce your code as well. as well as like just pulling out functions and stuff, because especially as you start writing more and more code, you'll find that you adapt functions and sort of cobble together commonly used functions. And to that end, I think a lot of people have sort of found value in the creation of their own R package. And so I maintain one that has, it only has like 5 functions in it now. It's just functions that I use a lot throughout my sort of research. And so one like plots a line segment onto an XY plot and gives the value of the correlation coefficient and the p-value. Super helpful, because sometimes I'm doing like exploratory data analysis. I just want to see like, is that relationship significant and what's the sign of it? And I want to draw a pretty line on it. And it's like, okay, so that is like a sanity check, but also sort of dives into the data structure a little bit. Another reason R packages are good is because it forces you to document your code. R packages have to have documentation. And you'll see, like, once you, I remember I was talking with Scott Chamberlain, who is he's the co-founder of, I'm pretty sure, our OpenSci. He's like, he's way above me in terms of our development stuff. And I was talking to him, an early grad student. And he said something like, oh, you should consider contributing to this, or consider building a package. And I thought, like, no, I can't do that. It's too difficult. And like, I'll tell you, it was really, really rewarding to actually sit down and realize that it wasn't that difficult to do. And so the DevTools package is what you'd want to start looking at. And I can also go over that if we have time in another one of the sort of Zoom lectures or something, to show you how to actually go about creating that skeleton R package. And many of the tools that you learn in this class, or that you have learned in this class, are transferable into maintaining an R package. And so Travis CI, remember when we used continuous integration? R packages are checked via continuous integration, or can be checked. So you can automatically run unit tests that alert you sort of if it's failing on a different R version or a different operating system. This is one thing I've hopefully mentioned. I know I've mentioned it numerous times, but hopefully have like mentioned it enough to where you guys and women and people are all going to do it. And that's don't set absolute paths. It's so annoying when you open up code. It's a small thing, but you see like a Dropbox link, or like you see like set working directory, user Dropbox, or like my documents. Like, and so this is the Linux example where I'd set to some project that's like some folder that's just sitting in my home directory, as if you have access to that. And so instead, you just have to assume that the person has the project folder and is in that directory, and then just make all your paths relative to that. Another one is force yourself to version projects. So it's really easy, especially when you're working alone on a project, to add, to commit, to push, and to actually keep versioning your project iteratively. Because you might think like, I only wrote a paragraph, or I only wrote 5 lines of code. It's not worth committing, but it is. Like, fundamentally, any progress is progress. Any progress you should track. This allows you to track the project progress. Do it, version that stuff. Because those 5 lines of code or text are 5 lines more than you had before. Yeah, I didn't really go super deep into open source and open access issues, except for a little bit on like licensing and things like that. But it's something that is important to me that we didn't really cover a lot. And so I'd recommend sort of diving into that and how it relates to reproducibility. And that's very, very general, but there's a lot of different sort of issues involved in paywall things and reproducibility in open science. Very interconnected web. But basically, like, if somebody hands you MATLAB code and says it's reproducible, it's not, because you might not have access to MATLAB. And so that's a little messed up. Like, so there's sort of like fundamental relationships between open access and open science in general and reproducibility that many people have pointed out in the past, but they're really interesting reading from a sort of philosophy of science and how we do science perspective, as well as like a functional, more practical perspective. These two I'm just gonna lump together. I remember I wrote these and I was just like, yeah, consider if you haven't played around with it or haven't been, I don't want to say like converted, been shown how cool it is, consider giving Linux, like even like a Ubuntu or whatever flavor of Linux you want, consider giving it a chance. Like install it as a virtual machine, play around with it, because a lot of the tools that I've gone over, they tend to play a little bit nicer with a Linux environment. Not unilaterally true, but like generally, that's what I found. Also, I went over LaTeX in the same breath as I went over R Markdown, and I know I gave way more preference toward R Markdown, but consider checking out LaTeX. It's pretty beautiful, especially for PhD students. I formatted my dissertation in LaTeX, and it saved an insane amount of time, because you probably know as well as I do that the requirements on dissertations are silly. You need a table of contents and a table of figures and a table of a list of tables, list of figures. All your references have to be cited in a certain way. LaTeX handles all of that for you. It'll handle all the margin issues and all that garbage, because you always have to have those certain margins, and don't like left justify or right justify, or because that's what matters in a dissertation. But yeah, LaTeX just does that stuff for you out of the box, and so it's pretty sweet. And a lot of times at universities, you can find LaTeX templates from previous students who have gone through the process and built their own template. And so I'm pretty sure that's what I did at UGA. I don't think I built my own. I think I found somebody in like physics or computer science that had cobbled together something really quick, and just adapted it to my purposes. So I would be surprised if that didn't exist at most institutions, but I don't know. Writing modular code is what we went over that a little bit. More like object-oriented programming. I guess it's like more like functional programming at that point. But if you find yourself writing the same code for multiple objects, it's not good practice. You probably just want to write a function that takes an object as an input and store it as some output, and therefore you can just apply that function across your different objects, if that makes sense. Also, just like I remember we went over like an apply statement or a function that it could do an apply statement for a bunch of different columns of a matrix, and you could hand it a function and say like, now I want the mean, no, now I want the standard deviation. And so writing a function that's general enough to handle multiple different inputs is very useful. I think I have there's two more. This one is just arbitrary, or not arbitrary, but it's like sort of obvious, and it's spaces. Don't use them in file names. They're really annoying, because all of a sudden you have to use these weird escape characters that symbolize spaces. Spaces they're broken. They're just cracks. Don't do them. Avoid them. And then finally, think about the long-term structure of your data. I've heard many people say like, we shouldn't be concerned about reproducible research in the long term. We should only be concerned about this reproducibility horizon of like 5 years. And I think that's bull. I think we need to consider longer term reproducibility, not as like a bar, like a low bar, but as like a gold standard. Like try to make your code as reproducible as possible for as long as possible. And one way you can do that is start thinking about data format issues. And so there's some data formats that just like don't exist anymore, right? And I struggled. Somebody handed me a database that was in some silly format that you had. It was proprietary. I couldn't get access to the software because I don't think the software like really existed anymore. And I had these great sources of data, and I couldn't access it because I didn't want to pay money to access data that somebody already they compiled. It wasn't silly. And so think about data format. So like XLX, XLSX, you probably want to avoid just in case Microsoft goes down, which it probably won't, but like it's also not that great or stable of a format, right? So like Microsoft Works files, I don't think are readable by most or any current Microsoft product. Do you guys remember Microsoft Works? It was good old days as me growing up. So keeping your data in format like CSV, TSV, etc., are just readable by everything, and that's unlikely to change in the future, barring any like insane advancements. I don't know. It's probably going to change in like 20 years, but it'll get you past that 5-year time horizon that people seem like it's a goal. So hopefully that lecture recorded all right. And thank you for watching. This has been a really great class. And yeah, feel free to email me with suggestions about what I should be changing, where you were confused, and I'm sure we'll talk about it in class as well. But yeah, I had a really great time. This course is something I've wanted to teach for a pretty long time, and I'm pretty stoked that I got a chance to do it. And this is the first time I've taught it, so it's probably going to change in the future. And so yeah, let me know if you have any feedback. And thank you. Bye.